Hi, everyone. Thanks everyone for joining me in person and online. I'm very honored to be able to present to you the work that I've been able to do during my PhD. Be able to be part of this type of work and to collaborate with a bunch of great people. I'm also grateful to be able to talk to you about my dissertation, the role of human activities in environmental change, because this is a dissertation that reflects my interest and spans from the science to policy to societal engagement spheres. So the big picture motivation of this dissertation is that global environmental challenges are multifaceted and that they require an integration of science, policy, and society to address them effectively. And this dissertation pulls in research from each of these spheres. So to provide an outline, I'm going to give a brief overview of greenhouse gases, and then that'll transition us into our first body of work, which is characterizing agricultural nitrous oxide emissions. And then I will talk about assessing international nitrous oxide policy, which will then transition us to talking about a collaboration effort in developing a framework for community engagement. Then I will conclude the dissertation presentation and provide a recap. And then I'll take questions from the audience. And then I will do acknowledgements at the end where I get to thank my entire support system that has helped me throughout this time. So let's kick things off. So I want to provide a brief overview of how the greenhouse effect works. So radiation from the sun warms up Earth's surface. And then at night, Earth's surface cools and it releases some of that heat back into space. Now, there are greenhouse gases that are in the atmosphere that trap some of that heat, which is why Earth is warm and cozy. Without an atmosphere, Earth would be a freezing planet. However, human activities are changing Earth's natural greenhouse effect by putting more greenhouse gases into the atmosphere, which trap more heat. And so human activities such as transportation, industry, and agriculture emit greenhouse gases. So this figure on the slide here shows the 2022 US greenhouse gas emissions. So you can see the different greenhouse gases that are emitted from 2022 on the top row of this figure, and then the total US greenhouse gas emissions by sector on the bottom row with all the little schematics. And so the more greenhouse gases that are emitted causes an increase in environmental issues. And we need a multidimensional approach to tackle on these environmental issues. So there are many layers of the atmosphere, and I want to focus on the troposphere, which is the layer closest to the Earth, and the stratosphere, which is the layer above. The gray layer in between these two right here is the ozone layer, and the ozone layer acts like the sunscreen for life on Earth. So it protects us from harmful ultraviolet radiation from the sun. So when humans emit greenhouse gases into the troposphere, they trap heat, and some of these greenhouse gases are better at trapping heat than others. And some of these greenhouse gases then get transported into the stratosphere, which is where they deplete ozone in the ozone layer. And again, that's the good ozone, which protects us. So one of these greenhouse gases is nitrous oxide, or chemically known as N2O. N2O is the third most important greenhouse gas behind carbon dioxide and methane, and it has a very long atmospheric lifetime. It also has a global warming potential, which is 300 times more harmful than carbon dioxide. And essentially, global warming potential is a way to measure how much heat a greenhouse gas traps in the atmosphere compared to carbon dioxide, which is the baseline. And then, like I just mentioned, nitrous oxide depletes the good ozone in the ozone layer. And so this brings me to our first body of work, which is characterizing agricultural nitrous oxide emissions. So the largest source of N2O is agricultural soil. Soils naturally produce N2O through two processes, nitrification and denitrification. And there are environmental factors such as soil moisture and temperature that affect these processes. In addition to environmental factors, the application of synthetic nitrogen fertilizer also alters these emissions. So when you apply nitrogen fertilizer, as shown in the animation, those compounds go into the soil and are taken up by soil microbes, which eventually end up burping out nitrous oxide into the atmosphere. Research shows that there's a large range in global emission estimates of N2O, and that there's an observational gap that exists. So this observational gap spans different spatial scales. So there are studies that use flux chambers at the meter scale to understand N2O from soil, but these flux chambers are spatially sparse. Then there are a limited number of tall towers that are used to represent the state level at hundreds of kilometers, and these are typically averaged over a month. However, this method is temporally poor and it doesn't tell you about individual farms. This photo here shows an aerial view of a tall tower monitoring site and its surroundings. So you can see the tall tower here in the middle and how it's surrounded by all of these different farms. So there's this huge observational gap between the two, which is where aircraft measurements come into play. With aircraft measurements, we can cover larger areas from the one kilometer to 100-kilometer scale. And because we cover these larger areas, it also aids in greater sensitivity to emissions from the farm to regional scales. And so we use aircraft observations in this body of work to try and provide more knowledge to this observational gap and to collect more data. So this brings me to our motivating questions. The big picture motivation is, how can we best use observations that guide practices that minimize the climate impact of agricultural activities used for food and biofuels? And then our more focused science questions are, what are the underlying spatial temporal emission characteristics we observe at these spatial scales? And are a small number of hotspots driving the bulk of emissions? So we conducted an airborne campaign called MAZE, which stands for the Measurement of Agriculture Illuminating Farm Zone Emissions of N2O. And the goal for this campaign was to measure nitrous oxide over agricultural fields in Iowa and Nebraska during the growing season in May and June. And so the states of Nebraska and Iowa are the states highlighted in red in that map. So we flew in May and June of 2021 over Nebraska and Iowa. And so this map here shows all of the different flight days colored by different dates. And the pixels underneath show the agricultural plots in these two states. So essentially Iowa and Nebraska are two agriculturally dense states. So in 2021, we flew 10 flights and the flight patterns varied between flight days. Then we revisited Iowa in 2022, and you can see all the different flight paths there. And so in 2022, we flew 8 flights and flight patterns were more consistent that year. So how do we use aircraft to measure N2O? Well, we have an inlet in the small airplane that we're flying, which is shown by the white arrow. And that inlet is connected to our instruments, which are located in the back of the plane here. And so we're able to fly over agricultural farms and measure N2O using 1 second frequency. And so a fun part about this type of data collection is that you get to fly on the plane as a flight scientist. So the first year that I went, this was my first flight. I fell very ill because maybe most of you know that I get very motion sickness. So this was our first year. However, when I went back, I took a miracle drug called Dramamine, and I felt so good that I was able to fly the plane for some of the legs. So let's get into the data. So I want to show you first the N2O spatial variability that we observed during the campaign. So on the screen, you can see the flight path, which is colored by N2O in parts per billion. So the lower value or the lower concentrations of N2O are in blue and the higher concentrations are in red. And here we have wind going to the southeast direction. I'm going to focus on this downwind leg here, which I outlined in the black box. So here is the N2O that we observed from left to right of this downwind leg. On the y-axis, you have N2O in parts per billion, and on the x-axis, you have distance in kilometers. We measured a background value upwind of about 338 parts per billion, which is the green line that I just put on the figure. So you can see that we see this broad enhancement over this entire flight leg, about 200 kilometers. But we also see enhancements within a 50-kilometer scale. So I want to zoom in with this red box here. So zooming in, we start to see smaller features on a smaller spatial scale within the 10 to 20-kilometer range. And then zooming in even more, we see even more smaller features at the 1 to 10-kilometer. So not only are we able to see an accumulation of emissions from the entire state, but we also see smaller features at scales within the 1 to 10-kilometer using aircraft measurements. Another thing that we unexpectedly observed was this correlation between N2O and water vapor. So again, we're looking at that same flight leg with the downwind leg outlined in the black box. So here I'm showing N2O versus water vapor. N2O is in black and it corresponds to the left y-axis, Water vapor is in blue and it corresponds to the right y-axis, and we have distance in kilometers on the x-axis. So we can see here that N2O and water vapor tend to follow the same variability in the first half of this panel, but then in the second half, the two sort of diverge. So when I apply a type 2 linear regression, we get a correlation value of R equals 0.3. Zooming in on this first half here, we see that N2O and water vapor are tightly correlated, and when I apply that type 2 linear regression, we get a correlation of 0.88. So here we note that water vapor is tied to soil moisture, and it's not due to the plants because of the timing of the flights when we went during the early growing season. And this correlation suggests that wetter soils are emitting more N2O. So then in order to optimize these emissions, we then use inversions to determine N2O fluxes. So typically studies will use a prior emission field and they run a forward model in order to calculate a modeled concentration. For this work, we have our airborne observations as measurements, and then we use a backwards transport model to calculate a posterior flux. And for our transport model, we use STILT, which is a Lagrangian particle dispersion model. So I'm going to walk you through STILT. So STILT uses meteorological data to transport air parcels backwards in time from a defined location, which is what you're seeing on the left. And it tracks each particle's sensitivity to surface fluxes. So the particles on the left are used to calculate a footprint, which is on the right, which defines the upstream area that influences the air arriving at a given location. So here I'm showing you what one of the STILT outputs looks like for our flight path that I was showing in the previous slides. So here's the footprint of that same flight that I introduced. And so we note that because this is running backwards in time, we give it a defined location, which is this corner right here for one of the examples. We note that the air parcels are coming from that direction. And what STILT tells us is that the redder the area of the footprint, the more sensitive our observations are to that air arriving to that location. So here, it's more likely that the surface emissions are coming from the redder area, which I pointed with the red arrow here, and then it's less likely here in the blue area. So then how do we take our airborne observations and our STILT outputs to generate surface N2O fluxes? Well, we use a Bayesian inversion framework to generate these fluxes. So a Bayesian inversion framework is set in Bayes' theorem, which essentially calculates the likelihood of an event using existing related information. And so the framework itself is a method to estimate unknown values from data, considering measurement uncertainty and what's already known. And the output is a range of possible numbers. So in our case, it's fluxes with an associated probability rather than just one single number. So I'm not going to talk through the equations, but these are the equations that we use for the inversion. And so when we generate these fluxes, we compare it to an upsampled descent model. And descent is a biogeochemical process model that simulates nitrous oxide emissions amongst other outputs. So I'm going to walk you through the inversion. So here we start with a prior flux, which is our upsampled descent model. We then use the STILT output, which is our backwards transport model, in order to calculate a modeled concentration. We then compare that concentration to observed concentrations, and this comparison defines an uncertainty for us. And then we do the inversion, all of those equations that I show. And we calculate the inversion multiple times, which gives us an ensemble. And that ensemble is our posterior flux. And then we compare our posterior flux to our prior flux, and these are the figures that I'm going to show in the next slide. So this figure here shows the average posterior N2O flux ensemble for a smaller area of interest compared to the upsampled descent model. So I'm going to walk you through this figure. So on the left y-axis here, we have our mean posterior flux. And on the x-axis, we have our flight days. So this black dashed line closest to the bottom of the figure is the descent average. And then the dotted smaller line is the descent max. And so we're using a violin plot, and a violin plot is a way to visualize data that shows the distribution of values. So the shape of the violin represents the density of the data at different values. So a wider section indicates a higher density of data points. Our smaller area of interest are highlighted in the dark boxes of the state of Iowa. So here for 2021, and then this yellow box here in 2022. So from this figure, we note that our daily posterior N2O fluxes are larger than the average value that's captured by the model, which is this black dashed line on the bottom here. We also note that our average posterior N2O fluxes are more comparable to the max model flux, but even then, we still see a higher magnitude of our posterior fluxes compared to the max of the model. The takeaway from this figure is that magnitudes are higher than the modeled N2O, and we see variability across flight days. And so then we ask ourselves, is a small fraction of farms emitting more? And this is what we're showing with this figure. So here I'm showing the percentage of total emissions from 25% of the domain. So the ensemble posterior fluxes are compared to the relative skew in the upsample descent model, which is the black dashed line. So on the left y-axis, we have the percentage of emissions from 25% of the domain. And in 2021, this is the descent model skew, which is about 48%. And then for 2022, this is the descent skew, which is showing that 25% of the area is emitting about 51%. So we note that the highest emitting 25% of the area in descent are responsible for 48 and 51% emissions, which are the black dashed lines, and that the highest emitting 25% of the area from our posterior fluxes is contributing 52 to upwards of 77% of total emissions, so a lot higher than the descent model. And so then we ask, well, is it always the same area that's emitting the most? Well, the answer is not always the same area emitting. So here I want to show you gridded fluxes for an area west of Des Moines. So this is where the white arrow is pointing in this red outline box. So here are gridded fluxes for back-to-back days where we had flights. So here we have day 1 and here we have day 2. So the brighter the pixel, the higher the flux we're observing or that we calculated for these 2 days. So we can see on day 1, it's a lot brighter, brighter pixels. And then on day 2, we see less of this brightness, the less hot spottiness. And so we note that the average posterior flux decreases 30% going from day 1 to day 2. And so key takeaways for this body of work is that we aim to understand how N2O emissions from agricultural lands in Iowa vary across time and space, and to what extent a small number of fields contribute to the overall emissions. We used airborne measurements of N2O across Iowa and the STILT model with a Bayesian inversion framework to estimate emissions. Our findings show that just 25% of areas contribute to 52 to 77% of total N2O emissions, with significant daily and location-based fluctuations influenced by soil moisture. And this research is critical for understanding climate impacts from agriculture, revealing that traditional methods may overlook key emission sources, and that enhanced measurement techniques like ours can lead to better emission models and informed mitigation strategies. So now I want to connect the science and the policy. So there have been some influential international treaties that have stemmed from scientific research, and that atmospheric science research was able to inform decision makers of the impact that these greenhouse gases had on the environment. And so there have been several global agreements that have been a result of scientific evidence. The first one being the Montreal Protocol, which was a result that scientific evidence showed that man-made chemicals were depleting ozone in the ozone layer, which again is the good ozone. And so the Montreal Protocol aims to phase out and phase down the production and consumption of these ozone depleting substances, mainly from refrigeration and air conditioning. Then there was the Kyoto Protocol, which was a result of growing concerns about global warming and the increasing evidence of humans' impact on the environment. And so the aim of the Kyoto Protocol was to reduce greenhouse gas emissions to 5.2% below 1990 levels. And then most recently, the Paris Agreement, which was a result of decades of scientific research and international collaboration showing the impact that humans have on the Earth and climate change. And so the Paris Agreement's goal is to limit the global average temperature from rising more than 2 degrees Celsius above pre-industrial levels by reducing greenhouse gas emissions. And so what came out of the Paris Agreement are these country plans called nationally determined contributions, where each country has to submit a plan, which started in 2020, that shows how they're going to reduce and tackle greenhouse gas emissions every 5 years and what their target goals are. And so this, again, is just to recap how scientific evidence has resulted in global agreements and informed policymakers to make these international treaties. And so integrating science with policy is important. Science informs environmental policy by providing data and highlighting knowledge gaps. And the accuracy of tools such as emission inventories, which are informed by scientific research, they depend on the quality of data and methods. And if we have faulty data and faulty methods, we're not going to have as strong of policies as we would need. And then there are scientific bodies, such as the Intergovernmental Panel on Climate Change, which compile climate knowledge for policymakers. And again, these uncertainties in data and data collection can limit the policy precision. But also on the other side, policy benefits from scientific insights, and it guides research direction and it sets funding budgets. And this brings me to my second body of work, which is where I assessed the policy framework of managing N2O emissions in New Zealand. So I think it's important, or I think a lot of us understand that it's important to regulate greenhouse gases in order to reduce emissions. And so as of June 2023, there have been 3,100 climate change laws and policies recorded worldwide. And so this figure here shows the total for each year of all of these climate laws and climate policies from 1995 to 2023. It's important to also mitigate nitrous oxide. So as I mentioned earlier, N2O is a powerful greenhouse gas, but it's often overlooked to its other counterparts, such as carbon dioxide and methane. Like I mentioned in the first part of the speech, the largest source of N2O comes from agricultural soil and fertilizer application. And as the figure on the right shows, annual emissions are on the rise. So as the population increases, so will food demand. And in order to supply that food, farmers and the agriculture sector is going to rely on things like fertilizer to help increase that crop yield. And so in this work, I'm examining the policy framework in New Zealand because New Zealand is set to become the first country to price agricultural emissions by 2025, making it a valuable study to examine what they're doing and whether or not what New Zealand is doing can be replicated on other countries that are dealing with the same issue. So a little background about New Zealand. The New Zealand Parliament holds legislative power. So that legislative body is called the House of Representatives. And there are two major political parties in New Zealand, the National Party, which is a right-leaning party, and the Labour Party, which is a left-leaning party. And what's really unique about New Zealand is its greenhouse gas emission profile. So the agriculture sector in New Zealand is over half of its greenhouse gas profile. So you can see there's a similar figure that you saw earlier, but this one represents New Zealand emissions. And you can see that agriculture is the dominating sector from that nation. However, there are challenges to regulating N2O. One is tracking agricultural emissions is a complex task. There's a vast number of small and diverse sources, and processes can vary widely depending on soil type, climate, and farming practices. And so I want to pull back this figure from the first section of the presentation, which you guys saw. And this figure shows that how variable the emissions can be across different days. And so we compared our fluxes to the magnitude of descent. And descent, again, is the model. And descent is used to inform emission inventories, which is a tool that policymakers use. So this just reiterates how important accurate data and methods are and how important it is to inform these emission inventories and models to be able to capture these emissions. Another challenge to regulating N2O is that no one-size-fits-all solution. So successful mitigation methods, they must be adaptable to different climates, different regions, different practices. And some mitigation strategies can be more costly in agriculture compared to other sectors. Agriculture is also a critical component of food security, and food security is a sensitive subject in politics. Nitrogen is also a critical component of fertilizers that boost crop yields. And like I mentioned earlier, if we have a growing population, we're going to have to feed that population. And so we're going to have to somehow increase crop yields. Another challenge to regulating N2O is that policies are perceived as threatening to the agricultural output and the livelihoods of farmers. So the farming lobby is typically against strict environmental regulations because it does impact their livelihoods. And also political decisions are also influenced by elections. Policymakers that have a huge agricultural support system behind them are not going to be the ones who are regulating for or promoting regulation to the agricultural sector, or else they will lose that fan base support for their election. So there are some policy tools that I want to talk about that governments can implement to mitigate greenhouse gases. One being greenhouse gas emissions pricing, or more commonly referred to as carbon pricing. So there are two methods: a carbon tax or an emissions cap and trade program, which is referred to as an emissions trading scheme. So a carbon tax or a carbon fee can assure a known cost for emissions, while an emissions cap can ensure a specific limit on the level of emissions. Then there's also emissions offsets. And this is a mechanism that allows businesses and individuals to compensate for their emissions by investing in environmental projects elsewhere that reduce the release of greenhouse gases. Another tool is government subsidies, where governments might provide financial support for low emission options. So if farmers want to invest in some low emitting technology, governments might be able to provide some sort of financial support to help reduce that cost. And then governments can also invest in research and development. And this investment can foster innovation that leads to reduced emissions. So governments can provide additional funding in order to grow research and development. All right, so let's jump into key climate legislations in New Zealand. So one key piece of legislation in New Zealand is the Climate Change Response Act 2002. And it's designed to address climate change and enable the country to meet its international obligations. This piece of legislation has been amended many times since it became an act in 2002. Some of the things that this legislation did is that it established the New Zealand Emissions Trading Scheme, which is what I'll talk about in the next slide. It also established a registry to track emission units, and it also created a national inventory agency and tasked it with documenting and reporting greenhouse gas emissions data. And also, it established a target for New Zealand to reduce its greenhouse gas emissions. First, net carbon emissions, they want to reduce to zero, and biogenic methane emissions by 24 to 40% by 2050. So this figure on the slide shows New Zealand's historical emissions from 1990 to 2021. So this top black line here is methane, this middle red line is N2O, and this growing blue dashed line is carbon dioxide. So essentially, New Zealand wants to reduce some of these greenhouse gases to zero within about 30 years. So the New Zealand Emissions Trading Scheme is the government's main tool for reducing greenhouse gas emissions, and it's set in a cap and trade principle. So it requires measurement and reporting on greenhouse gas emissions, and businesses that emit must surrender one emission unit, is what they're called, for each 1 ton of emissions emitted. And so the emissions trading scheme limits the number of emission units available over time, because that is how they reduce emissions from businesses. The money from the emissions trading scheme goes into the Climate Emergency Response Fund, and this funds initiatives that reduce emissions and vulnerability to the impacts of climate change. One notable exception to the emissions trading scheme is the agriculture sector. It's not subject to the ETS. It does have a reporting obligation, but it does not have to participate in the cap and trade program. And then the Climate Change Response Act legislation says that the agriculture sector must have a carbon pricing mechanism by 2026, either through the emissions trading scheme or an alternative system. And so there's been a proposal of a different approach to pricing agricultural emissions. And so one of the disadvantages to the emissions trading scheme of agriculture being priced is that it would not recognize individual farms for their actions to reduce emissions, and it does not treat nitrous oxide and methane differently. So in May of 2022, New Zealand published its first emissions reduction plan. And this plan introduced an agricultural emissions pricing mechanism by 2025. It also established the Center for Climate Action on Agricultural Emissions. And basically, this is a center that is focused on developing lower emitting technologies for the agricultural sector. So the government selected the Primary Sector Climate Action Partnership, the Hiwaka-Ekanoa proposal, and this proposal is the alternative model to pricing agricultural emissions. This proposal is a partnership between the government, the primary sector, and the Maori people, which are the indigenous people of mainland New Zealand. And so their recommendation in this proposal is to implement a farm level split gas levy. So farm level, the advantage to this is that it would recognize individual farms, unlike the emissions trading scheme. And then the split gas would treat nitrous oxide and methane differently, which would be different than the emissions trading scheme. So I'm going to walk you through of how the Hiwaka-Ekanoa system would work. So I want to note that farmers are responsible for reporting and paying for their own emissions based on farm-specific data via an emissions calculator. So I want to reiterate how important it is. So we saw in the first section of this presentation that the farm scale is an important scale to understand emissions, and that informing emissions calculators to be accurate and precise is also important, so then people aren't being pinged by incorrect emissions from their farms. So farmers would report their short-lived gases, which is methane, and then they would add the cost of their long-lived gases, which is nitrous oxide and carbon dioxide. Then they would subtract incentive discounts. So if they're implementing some sort of technology that is lower emitting than other technologies, then they would subtract this part. And then they would subtract any sort of sequestration that is happening, such as forestry. They would combine all of those to get a farm level levy, essentially a tax that the farmer would pay. And this money would go towards paying for the system and paying for the development of agricultural technology that is lower emitting. And so what is the current status of this agricultural emission pricing proposal? So during the formation of Hiwaka-Ekanoa, the Labor Party was in control. And again, the Labor Party is a left-leaning party. So at the time, Prime Minister Ardern said that the plan would be released in early 2023. She then also resigned around the same time in early 2023, which then called for a New Zealand general election. So between then and the general election, Prime Minister Hipkins was nominated from the Labor Party to replace her seat. And in August of 2023, he said that pricing agricultural emissions is crucial, but that decision would be left to a future government. Then in November of 2023, New Zealand had its general elections, and that's where the National Party took majority. And again, they're the right-leaning party. And so the current government, which is led by Prime Minister Luxon, have vowed to initiate pricing on agricultural emissions no later than 2030. However, the party has committed to repealing sections of the Climate Change Response Act that would enforce agriculture into the New Zealand emissions trading scheme from 2026. So they have delayed this process. And there's currently speculation that the Hiwaka-Ekanoa partnership is no more. And then this article came out just last Thursday that says that the government of Prime Minister Luxon has made sweeping cuts to climate projects in its first budget with no new significant environmental investments. So we're seeing a huge delay and a huge cutback on the advancement of environmental policy progress in New Zealand. So can this framework be applied elsewhere? Well, it's challenging because there's two sides that we need to examine. First, the applicability of the framework abroad. Can this framework be applied to other nations? And also the robustness of New Zealand's own policies. Are these policies manageable, but also are they aggressive? And what kind of technology and data are they relying on? Because if it's faulty, then this policy won't be as strong. So one of the challenges is that agricultural production is an economic backbone for many nations. So I've added the percentages on the slide, and these percentages provide an indication of how much agricultural production contributes to the overall economic output of countries at different economic levels measured by the gross domestic product. So we can see that low-income countries heavily rely on agriculture to support their economic output according to their gross domestic product. Another challenge is that not only are we trying to reduce greenhouse gases, but we're also trying to produce food for growing populations. And this can cause a raise in food prices, which would then yield to a higher risk of food insecurity, which a lot of developing countries are already dealing with. Also, one of the challenges is that there are different political structures from one nation to another. So, as I mentioned, New Zealand has control in the House of Representatives, and that is their main legislative body. But countries like the US, where we have a two-chamber system, the House and the Senate, it's a lot difficult to try and pass environmental policies through both bodies of Congress. Policies are also influenced by different coalitions, lobby groups, and public opinions, which add to the challenge. And there are different climate goals for nations. So we've been able to see this not only in New Zealand, which I just talked about, how the Labour Party and then the National Party took over and slowed down the transition of agricultural pricing, but also transitions of power have slowed down progress in countries like the US, where we saw climate policies under the Obama administration. And then we saw a lot of repeals of these policies with the Trump administration. And now we're seeing policies try to be reenacted by the Biden administration. And the Hiwaka-Eka-Noa framework is an example of how this responsibility will fall on farmers. And this would cause additional burdens to farmers and their livelihoods. And then also some countries have a culture that's ingrained in agriculture, like the US, and this would make it challenging to kind of apply agricultural pricing. So the key takeaways in this section is that addressing nitrous oxide which is a potent but often overlooked greenhouse gas, is crucial for effective climate policies. New Zealand was set to become the first country to price agricultural emissions, but it's currently delayed. But yet this case is still valuable to understand how they approached it and what their plans were to do with it. And New Zealand also, it's a greenhouse gas profile I showed earlier that agriculture represents over half of the emissions profile of the country. The Hiwaka-Eka-Noa proposal offered an alternative to pricing agricultural emissions, and their recommendation was a farm-level split gas levy. And then New Zealand's response and framework presents challenges for other countries, and like I just mentioned, economic backbones, the politics, and also climate priorities for different nations. So now I want to connect the science and the policies to societal engagement. So sharing expertise with decision makers on all scales can lead to more targeted and effective policies. And these policies can resonate with community needs and values. Accessible language and the translation of complex findings are essential for empowering communities because it allows scientific knowledge to be integrated into community initiatives. And this brings me to a collaboration. This brings me to this body of work, which was a collaboration within the department to develop a framework for community engagement. So climate change, I think we can all agree upon, is that it's one of the most complex issues of our time. It requires an approach that's beyond traditional scientific boundaries and an integration of knowledge across many sectors and disciplines. So this figure here just shows how physical science engagement can often be slow to work and the difficulty of it to apply to small scales. So typically researchers will identify a problem and then conduct research to try and tackle this problem. And then that research will then yield publications, and then we're stuck in sort of this like repeat cycle. And sometimes those publications will trickle down to serve as reports or congressional testimony or inform policy decisions. So these environmental issues, they require geoscientists and community partners to co-create solutions that align with community priorities at the local and regional scales. So scholars have established frameworks on collaborative knowledge creation between academics and non-academics. However, challenges still exist. These challenges include that climate science is usually done in isolation from the societal scenarios where it needs to be applied. Also, challenges from a communication barrier or conflicting interests or competing policies make it difficult to collaborate. And then also there's this lack of systemic guidelines and coherent integration between science, policy, and practice. And so one way of achieving this collaboration is using an integrative approach known as transdisciplinary research. And so transdisciplinary research acknowledges the importance of including non-academic partners, So this figure here just shows two sides of knowledge, academic knowledge and conventional knowledge, and that all of the participants are working towards a unified goal. One example is to co-produce knowledge with community partners, because science is then translated into more accessible forms and integrated into community initiatives. And this method is emerging as a pivotal strategy for integrating real-world perspectives into climate science decisions. However, there are institutional barriers that exist which limit the deployment of these transdisciplinary approaches in academia. One being that physical science programs prioritize the production of new knowledge over more applied problems, and that PhD programs prioritize academic publications over outcomes that may be more usable to partners. So a core of a PhD is rooted in peer-reviewed publications, and these publications are rarely written for or accessible to community partners. The literature on the frameworks on how to engage is often also inaccessible to climate scientists. And that leads me to the motivation. So students are not currently trained in the skills needed to engage in dialogue with communities. And this led to a student-led effort to reduce institutional barriers and provide training opportunities in community engagement geared towards physical science students. This was a collaboration between students and faculty within the Department of Climate and Space Sciences and Engineering to create a hands-on community-focused pilot course. So when graduate level courses are developed, we have traditional curriculum. And typically this traditional curriculum is rooted in generating new knowledge, which then results in a minimal attention to skills needed for engagement. And again, traditional curriculum is mostly heavily relying on peer-reviewed journal publications. Although students have opportunities to engage and contribute to community-focused projects, many of these opportunities are extracurricular, they're uncredited volunteer efforts, and there's no systemic training, structure, and/or academic support. And so we want to bridge the two. And so we developed a graduate level course to give students opportunities to apply climate knowledge in a local community setting. So this was a single semester course. It was 4 credit, and this was initiated from an interest email in fall of 2020. And so the course objective was to develop the necessary skills for PhD students to apply their scientific expertise towards solving community scale climate problems, which involved collaboration and project design skills within a non-academic setting. So the key is to find and establish trust with a non-academic partner, but this can take a long time. And so finding a partner for us was very difficult because we were dealing with the COVID-19 pandemic, which halted all in-person interactions and forced us to move virtually. So it's very hard to meet new people virtually. We also didn't have any funding to compensate our community partner because they're taking the time out of their day to work with us. We also had a time constraint where we only had a single semester to develop this partnership and do a project. And then as students, we also lack professional credentials. We don't have PhDs to our names, and so we're less likely to find a partner who would trust us to do a project of their interest. And so we relied and worked with the University of Michigan's Edward Ginsburg Center to help us find a partner. And the Ginsburg Center is a community and civic engagement resource center on campus. They have a very expansive network of community partners, and they help connect students, faculty, and staff with these community partners. And so our partner ended up being the Washtenaw County Water Resources Commissioner's Office, and they're a local government office in Michigan. And so the Water Resources Office wanted to expand their rain garden outreach program. And so rain gardens are shallow depressions filled with plants, and they're designed to collect and filter water that flows off of hard surfaces as shown in the image on the screen. And so when it rains, these rain gardens infiltrate runoff and remove pollutants. And so the Water Resource Office wanted us to create an analysis of high priority locations for rain gardens in Washtenaw County. And Washtenaw County is the red box highlighted in the map on the screen. And so they have 3 criteria for us. 1, to prioritize areas with degraded water quality. 2, to prioritize underserved populations. And 3, prioritize the improvement of wildlife habitat connectivity. And so we used ArcGIS to create data sets because ArcGIS is the program and data analysis software that our partner uses. And so our analysis was modeled after two studies which predicted water quality outcomes from land use scenarios and combined water quality, social vulnerability, and air quality metrics. So here I'm showing you a workflow chart of what our semester looked like. So early in the semester, we identified a community partner to work with. And then after meeting with our partner, we identified our climate project that we were going to do, which led us into doing a literature review on rain gardens and the type of analysis that we might need and what kind of data we needed. And so this all resulted in discussions amongst our group on how we wanted to construct our methodology, what data to identify, what training do we need, because not all of us were well versed in GIS. And so I want to highlight in the yellow box, this is where we really engaged with our community partner. This is where we were able to go back to our community partner with questions, ask them about clarification about the project, make sure that we have the right data, so on and so forth. So then after we got set with our project and did our analysis, we provided our community partner with preliminary results and a preliminary progress report. And in this time period, when we showed or shared with them a preliminary report, we noted that one of the analysis that we were doing in this project was a precipitation projection, which usually is on a scale of hundreds of years. And we learned here that this type of projection was less important to the community partner because of such of a long time scale that these projections revolve around, and that our community partner worked on a much shorter time scale. And so this was really important information for us to learn in order to inform our project. And then at the end, we presented our final work and our final report to our community partner and provided all of the data to them. So now I'm going to show you the figures that we created, but I'm not going to talk in depth about these figures. If you're interested in reading the technical report on how we came up with these figures and analysis, there's a link at the bottom of this slide. I encourage you to read. So I'm going to show you three different GIS layers for the three criteria, and the higher priority areas of our rain garden site selection are going to be in the redder, warmer colors. So first is our water runoff metric. And this metric focused on the impermeability of surfaces in different areas of Washtenaw County. Our second metric was looking at social inequality, and this figure highlights underserved communities and areas of where we should prioritize rain gardens. And third, we looked at wildlife corridors where forested areas would connect local wildlife in Washtenaw County. So I'm zooming in on this third map so you can see the line corridors where we've connected forested areas and figured out higher priority areas to connect that wildlife. So some of the outcomes that we learned from this project is working with a community partner was a new and valuable experience for us. We produced GIS layers and reports and presentations to the Water Resources Office, and this class is now offered as an elective to undergraduate and graduate students. Some of the lessons that we learned from this project is that for long-term sustainability, we need to develop support mechanisms so initiatives become more permanent and structured. And we also learned that our project evolved to be less dependent on climate projections, like I mentioned with the precipitation projection. And we also learned that non-climate factors such as land use often have a greater impact on local issues than climate projections. So that brings us to the end, where I get to provide you a recap of everything I just spewed at you. So in the first body of work that I shared, we characterized agricultural N2O emissions. So N2O emissions from croplands play a significant role in global warming, but modeling and observation challenges still exist. We combined our airborne measurements with our backward transport model STILT and also our Bayesian inversion framework to get at an estimate of emissions. And we showed that 25% of our observed area was responsible for 52 to 77% of the total emissions. I then connected the science and the policy. And so in the second body of work, I talked about how important it is to address N2O for effective climate policies. And I investigated New Zealand's pioneering approach to pricing agricultural emissions. But I also mentioned that politics and challenges to mitigating N2O presents barriers to this type of policy development. And we saw that in New Zealand, it was slowing down this approach. And then I connected the science and society and the policy to society, where in the most recent section, I talked about how a collaboration effort to develop a framework for community engagement resulted in a pilot course for students to partner with a local community partner on climate solutions, where we produced GIS layers and a report. And it was a successful student-led initiative that bridged the knowledge gap between academic research and practical community applications. So to leave you with this, solving our environmental challenges truly depends on a partnership between science, policy, and society, and together can pave the way towards a more sustainable future. And with that, I will take questions before I do my acknowledgements. Okay. It's fine. We're fine. Okay, so I've prepared a written statement because because it's easier to read than try to think of words while you're crying. Okay. Okay, I stand before you today. Okay, I need someone else to read this. I stand before you today filled with a deep sense of gratitude, aware that the journey that I embarked upon leading to this very moment was far from a solitary pursuit. I stand here as a testament to the power of the community, to the collective strength and unwavering support of my own personal village, and I stand here because I never truly stood alone. So I want to give a quick thank you to everyone, friends and family, who have joined me in person and virtually from the very early hours of the West Coast to those overseas. Although this presentation covered most of the research that I've conducted or been a part of during my time here at UMich, it doesn't include all of it, nor does it include the extracurriculars that I've been a part of, as I talked about with the traditional curriculum. So I want to highlight some of my contributions, and then I want to thank the support system that cheered me on through it all. So while as a PhD student, I've been a first author on 4 papers, one which was recently submitted, and the second which is technically pending acceptance according to the editor after the second round of revisions. I've also been a co-author on a paper and a policy brief, which won second place in a national competition. I've given 6 oral talks, 2 poster presentations. I've served as a panelist on 3 policy panels, and I've made 2 radio show appearances. I've led or been a part of 7 university organizations and committees, which have taught me leadership skills, teamwork skills, project and time management, to name a few, as well as all of the friends and networks that I've been able to make. And then for those who don't know, I've grown to become quite passionate about science policy that I want to make in my career. So I've been able to obtain a graduate certificate of science, technology, and public policy from the Ford School, and also participate in the AGU Voices for Science program this past year, to name a few. And these experiences have helped me expand my knowledge of the science policy process, and I've been able to meet a lot of great people throughout these opportunities. So what's next with me, or what's next for me? So, and this only depends if my committee lets me pass. I will be moving to Washington, D.C. as the American Geosciences Institute William L. Fisher Congressional Geoscience Fellow for the upcoming year, where I will be working for a congressional member on science-related issues. So this kind of gets at that last online question about how I'll be participating post-graduation in community work. I'll be getting to meet a lot of constituents and community members and talking with lobby groups. Yes, so that's next for me. And so I'd like to acknowledge and thank everyone in my village that has helped build and strengthen the foundation on which I stand upon today. Those that have supported me, mentored me, believed in me, trusted me, laughed, and danced with me. Thank you just doesn't capture it all, but it's the best that I can do. Thank you to my K through 12th grade teachers, my coaches and friends for believing in me and supporting me in STEM. To my College of Idaho professors, mentors, bosses, staff, and friends who supported me into the research opportunities that taught me what research and fieldwork were like. To the wonderful people in NASA SARP 2017 and the life-changing summer that made me interested in pursuing atmospheric science. And to the brilliant colleagues, office mates, advisors, and friends during my gap year at NASA Goddard who trusted and supported me. Thank you. I'm grateful to both the National Science Foundation Graduate Research Fellowship Program and the Rackham Graduate School Predoctoral Fellowship for awarding me fellowships that have fully funded my PhD. I'd also like to acknowledge the additional funding sources for letting me travel to really cool conferences, funding our research flights, or supporting university events that I helped develop. Thank you to all of my collaborators and co-authors and research support. Without you, this work would not be possible. Thank you to my committee members for serving on my committee and for the research guidance, collaboration, and administrative reform that I have been so fortunate to have been a part of. Thank you to all of the faculty, the educators, and staff that have been able to engage with over the years. I hope I brought a smile to your face. The path to a PhD is strenuous. It's fraught with intellectual challenges, emotional ups and downs, and countless obstacles that at times seem insurmountable, like when the COVID pandemic hit us 7 months into my first year of a PhD. Yeah, that was awful. It demands perseverance and an unyielding drive, traits that are undoubtedly important, yet not sufficiently so when devoid of external support. A PhD journey fundamentally is a communal effort imbued with the care, wisdom, and strength of each person who has been a part of it. First, the infamous Court group. I would like to thank my advisor, Eric Court, for helping me cross this finish line and for bringing together such a wonderful group of people. I'm also grateful to all of the Court group members and honorary members for being the most sociable group in the department. Your guys' support and the laughter we shared, often loud enough to echo down the hallway, added so much joy to my journey. I owe a special thank you to Jenny Plant, our research mom. Her willingness to lend a hand, be my therapist, and answer questions have been immensely helpful. The Court group is truly something unique, and the memories we've created together will always be held close together. This is so embarrassing. Okay. Next, I am immensely grateful to the volleyball community, which I have had the privilege of helping span across campus. My heartfelt thanks go to my volleyball teammates from campus and the Ann Arbor City League, including Pizza Calzone, No Tie Pals, volleyballs, and team subs. Volleyball has been my rock through sunshine and rain, and your camaraderie has made countless volleyball days enjoyable. Thank you for every serve, set, spike, and beep, boop, bop moment of laughter. To my many friends, both near and far, whose numbers are too great to list and whose individual acknowledgements could never do justice to the depth of my gratitude, I offer my sincere thanks. Thank you for nourishing me, for your hugs, and for comforting me in times of sorrow, for FaceTiming joy into my days, for dancing through life with me, and for your unconditional love. I cherish all of the memories we have created together. I owe a profound debt of gratitude to my mom, Snežana, my baka Milica, for their unwavering support of the Dacic women. My mom, a single parent, has made countless sacrifices in order to give us a better life and to move us to the US because of a war that tore up her home country. Even though times were tough between us in the past 5 years, words cannot fully express my appreciation for your love and dedication, but please know that I am externally thankful for everything you have done. Hvala vam, mama I baku, za vašu ljubav I sve što ste učinili za našu porodicu. Volim vas obje. And last but not least, to my car Bertha, the only entity capable of transforming my paychecks into mysterious noises and creative curse words. I salute your tenacity, and my ever-depleting bank account thanks you. And to the Ann Arbor Railroad for its reliable companionship on many late nights. Choo-choo. Thank you all from the bottom of my heart for everything.